next phase, the arm. So in arm, we are going to have the general classification based on 3 joints. So the 3 joints as we start can be prismatic, 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 revolute, prismatic, prismatic, revolute, revolute and prismatic, and finally you will find all 3 joints to be as revolute. So the classifications begins with 3 joints to be as linear. After that, the base joint is being replaced by a rotatable joint, and the next classification we have 2 rotary joints and 1 prismatic joint, and at the last we have 3 joints with all in rotary in nature. So this is all about the classification based on arm configurations. We say it as arm configurations. These are all arm configurations. We name it as Cartesian robot if it contains 3 joints to be as linear, and at the last we call it as articulated arm configuration since all the joints are rotary, which is nothing but your human arm. Your human arm contains all 3 joints to be as rotary. So the beauty of having the joints as rotary is you can perform a linear action even though the 3 joints are rotatable. So performing a linear movement with the help of 3 rotatable joints is the beauty behind articulated arm. So the second one is called cylindrical robot. The third one is called spherical robot, or we can say it as telescopic configuration. Okay. So I remind you this again. So the subclassifications based on the arm will be upon the 3 joints. So the first column represents joint number 1, second represents joint number 2, third represents joint number 3. So 3 joints. The nature of the joints classify the robot with respect to different workspaces. So what is workspace and how do we classify that? It all depends on the classifications what we have right now. So the workspace, if you ask for the Cartesian robot, will be a cuboidal. So you see, you will have a cuboidal structure and this will be your workspace. Okay, this will be the workspace for the Cartesian robot. In cylindrical robot, the workspace changes. A cylinder is being a 3D, 3-dimensional volume of cylinder will be the workspace. And for the spherical robot, again, as the name suggests, the workspace will be a sphere. And for the articulated arm has the maximum efficiency in covering the workspace. So just like your hand, you can wave around, you can reach the points, intermittent points. It has many lesser dead zones comparatively to the above 3 configurations. So the robot companies prefer articulated arm. Any robot type if you choose, it will have articulated arm configurations to be definite. So in 3D printers you can see about Cartesian robot configuration where the 3 joints are linear, and followed by in cylindrical and spherical robot. These are customizable one in transport and logistic industries. You will find these 2 robots, cylindrical and spherical robot, and all the industries will carry articulated arm configuration. So this is all about the classifications based on arm. Now coming to the terms which are being used in robotics, we talk about degrees of freedom. Number one, degrees of freedom. These are general terms. I am not diving into the um, more theoretical parts. This is all about understanding the phenomena of robotics. So, the first term we will use is degrees of freedom. After degrees of freedom, we will study about workspace. Then we will study about dead zones. Then singularity. So, degrees of freedom is the independent movement a robot can make with respect to each joint. Say for example, if I have my human arm to be as taken as an example, this human arm contains three primary joints as I said before, starting from the shoulder, knee, knucklehead and followed by the wrist. So, we have three primary joints. So, these three primary joints has three independent actions. So, hence the degrees of freedom will be taken as 3. So, this is for your understanding. And workspace, the workspace, the maximum reachable limit and the minimum retraction limit that a robot can possess. It will confine into a volume and that volume will be considered as workspace. And next, dead zones. So, dead zones are areas where a robot cannot move or becomes immobilized, where it can be in the inner limits, it can also be in the stretched limits, extendable limits. All comes under dead zones and followed by a condition called singularity. Singularity is a term, a good term that is need to be understood. So, singularity is where one of the joint, at least one of the joint fails and becomes immobilized, which again goes to a dead zone part where the robot is loses its degree of freedom. So, possibly you might have understood things. Degrees of freedom is all about the independent axis movement a robot can make with respect to a joint, and followed by the workspace, the workable area, which are confined to the joint movements, which are confined to the flexibility, and third, dead zones where a robot cannot reach to an extreme as well as to the inner limits. And the singularity is a condition where a robot loses a degree of freedom, at least one degree of freedom. It may be multiple. Even so, if it loses a single degree of freedom also, we call that case as a singularity. So, this is all about the terms. Now, we have completed ARM configurations. Next, we are moving towards end effectors. And before that, we also have wrist configuration. This wrist configuration is similar to that of an ARM configuration, but the joints are present consecutive. So, you will find a wrist can contain three movements in particular. We call it as roll, pitch and yaw. This roll, pitch and yaw is nothing but a consecutive of three joint actions which corresponds to the wrist configuration. Okay. So, all three are again with respect to a different axis of rotation, still they are rotatable joints. And now coming to the end effector. So, what is end effector? So, end effector is a point or a tool where we are going to make this robot customized for an application. Say for example, if I am working for a painting job, if I employ an ABB CBR 15,000 robot for the painting job, then the painting tool which is put after the wrist will be considered as the end effector. Say if it is a welding job I am going to pursue, then the welding tool will be considered so. So, the end effectors are customizable. It may be a gripper, it may be a two-way gripper, it may be a pneumatic gripper, laser cutting tool, all depends with respect to the application. So, a user defines what end effector should be chosen. So, the whole structure, the physiology of the robot contains base, arm, wrist and end effector, and the user decides what end effector must be chosen with respect to the area of application. So, now this is all about the classifications and the physiology about the robots. The next phase what we are going to see is we are going to study about the science behind robots. How a non-movable body part, which is link, when connected to a joint becomes a kinematic chain, and how we are going to operate this kinematic chain. Say for example, I have a base, a fixature for the robot. This is the first joint. The dot which is made as A is the first joint, and the dot which is made as B is the second joint, and I have one more joint called C which focuses to the end effector. So this is my end effector. So I have 1, 2, 3 joints. We talk with respect to fundamentals. We may have many degrees of freedom. Again, I'm saying it is not restricted to only 3 degrees. When we include risk configuration, still we have higher degrees of freedom, maybe up to 6. Any industry robot nowadays will have at least 6 degrees of freedom. So 6 independent movements. So in general, for understanding the purpose, we have an example diagram which contains 3 joints A, B and C, and followed by that an end effector. So what I try to say here is the science behind robotics starts with understanding about kinematics. We have two kinds of principles being employed. For understanding the motions, we require two kinematic procedures. One is forward kinematics, and the second one is inverse kinematics. So we are not going to dive more into these phenomena because these are all separate concepts which can be taken as a separate content in a different class. Now we have two contents we are going to discuss. One is forward kinematics and the other one is inverse kinematics. So what is forward kinematics? Knowing the displacement variables with respect to the joints, if I am able to compute where the end effector is being located, we call it as forward kinematics. Again, I am saying the joint variables, if it is known, 1, 2 and 3, if it is known, I will be able to plot where this end effector is in the 3D space, x, y, z coordinate. We call it as forward kinematics procedure. So in inverse kinematics, rather of knowing the displacement variables with respect to joints, we will have the final 3D space coordinate. With respect to the 3D space coordinate, we try to adjust the joint variables. So it is a complete opposite process with respect to forward motion. We call it as inverse kinematics. So this is all about the science of motion in robotics, in industrial robots in particular. So in forward, we know displacement variables. So this displacement variables gives me end effector position in 3D space. In inverse kinematics, we know the 3D position of end effector. We find displacement variables of the joint. So this is all your understanding about the motion behind robotics in industrial robots. So displacement variables, if I know, I am able to compute the position where the end effector is being located. We call it as forward kinematics. Knowing the end effector's position, if I am able to recompute the displacement of variables in joints, then it is called as inverse kinematics. So this is all about the study of motion with respect to industrial robots. Now the next thing what we need to know, how we will compute this displacement variable, how we know the end effector position, all will be done through a matrix called HTM. So this HTM is called as homogeneous transformation matrix. It is a 4 by 4 matrix. So the whole matrix is 4 cross 4. In that, we have first 3 cross 3, then a 3 cross 1, then a 1 cross 1, and 1 cross 3. Okay. So 3 cross 3 gives me the rotation, or we say it as rotational matrix. This we call it as translational or linear movement. This is for vision, perspective of vision, and this is for scaling. So a homogeneous transformation matrix contains all these phenomena with respect to the end effectors rotation, translation, followed by vision and scaling factor. Preferably, we will have this matrix understood with respect to rotation and translation. That is, if I have a joint movement from A, if I have a joint movement from B, it may be either rotational or translational. If I have a joint movement from C, it can also be rotational or translational. If I combine together, what will happen to my end effectors position? That is composed with the help of this HTM, homogeneous transformation matrix. For computing this, we need to know about DH rule, Dinowitz and Hattenberg's principle, or Dinowitz and Hattenberg's theory. So Dinowitz and Hattenberg together has created a principle behind in computation of the displacement variables into a table, and after which it can be projected to a homogeneous transformation matrix. So this is all about the basics behind understanding the motion of industrial robots. So we need to learn about more mathematics here. So the mathematics starts from representing an equation or in representation with respect to a matrix. All is required for learning. So this is one part where we will understand about knowing the displacement variables where the end effector is being positioned in a 3D space. The next aspect is, if I am moving the robo from one point to another, will it move randomly or will it have a path constraint or will it have a trajectory? So we need both understanding about what is path as well as trajectory. So in robo, we talk about path planning with respect to acceleration and velocity. So the next part is, after forward and inverse kinematics, we will study about path planning, trajectory. So what is path? Path is a series of points which joins from starting to the destination. Okay, so we find intermediate points in between. So this categorizes how the path is being put forward. So I can choose a different path for different movements, but is that movement feasible? So a robot application area, a workspace, the confinement, all depends with respect to the customer's requirement. So the customer's requirement may change, an obstacle may be present in between. So if that is the case, I need to choose a different path for the robot. So all comes under path planning. What is trajectory? Again, a path being governed, knowing the future location, predicting the future location with respect to acceleration and velocity along with intermediary points, we call it as trajectory. So for these, we require polynomial or polynomial representations. What is polynomial? You know about polynomials. A degree polynomial of 1 will have an equation of y is equal to mx plus c, where the power of the variable x is 1. The degree is 1. So if I need to go for a rather higher degree of polynomial, I will go for ax square plus bx plus c, which stands to be the 2-degree polynomial. If I go for a 3rd-degree polynomial, then again ax cube plus bx square plus cx plus d is equal to 0 is a representation for understanding the degree of polynomial. Okay, so this is for understanding. But for creating a path, which degree polynomial is required. So I will require a cubic polynomial as a minimum if I am creating a path for the robot to function. So it will require a 3-degree polynomial or a cubic polynomial. Why a third degree polynomial is required? If you ask me, say for example, I have an equation called some ax plus b is equal to 0, which is a degree of 1. If I differentiate this with respect to x, why I differentiate, I will tell you. So dx by, or we can say it as in terms of at plus b. So this is an equation x continues to at plus b is equal to 0. If I differentiate the x equation with respect to time, what I get is a. If I double differentiate that, the value will be 0. Supposingly, if I take a second degree polynomial like this, ax square plus b, at square plus bt square plus c is equal to 0. This is representing a x equation. If I differentiate that dx by dt, I get 2at plus b. If I double differentiate that, I get 2a. So this represents the first derivative, differentiation of the equation with respect to time. Upon the first derivative, I get a constant in 1-degree polynomial. In second degree polynomial, I get a constant here at double differentiation. So this should not happen. Why? So the first differentiation with respect to x, if x is notified as displacement, if it is a straight line, I may have y is equal to mx plus c. If that is a straight line I am representing, if I differentiate that, which gives velocity terms, displacement if differentiated gives velocity terms. If I double differentiate that, it gives acceleration terms. So look at the first degree. So if I am having a straight line, if I differentiate that displacement what is being given, I get the velocity as constant, which is not permissible. And if I double differentiate that, the acceleration becomes 0, which is also not permissible. So if I go for 2-degree polynomial, I will have velocity to pertain with respect to time, whereas acceleration becomes constant, which is not permissible. And that is why we require a cubic polynomial for representing a path. So a path is always being confined with respect to a cubic polynomial, which is a degree of power 3. So if I have power of degree 3, I will have the differentials for the first order differentiation as well as the second order differentiation, which is nothing but your velocity and acceleration to pertain with respect to time, rather it becomes a constant or a 0 value. So this is all about path planning. So if I am creating a path for the robot, this path of the robot should have a starting point and destination, which is governed by the equation, and the governing equation should be a minimum of cubic polynomial. So in path planning, we also have a smooth transition planning, we also have a spline trajectory planning. All these are um, subparts that need to be learned when we go for path planning techniques. So again, I am giving you a clarification that if I am planning a path is nothing but a starting and destination point governed by intermediary locations, whereas a trajectory is all about again the future prediction of the next location with respect to velocity and acceleration. It also governs path, but we are very much specific towards velocity and acceleration. So whenever you design a path for the robot, you require velocity profile as well as acceleration profile with respect to intermediary points. So this is all about understanding the robots with respect to path planning. So after this, what I need to study, if you ask me, I have studied about forward kinematics, I have studied about inverse kinematics, I have also studied about path planning. So is that it all? Is that completes the understanding about robots, each and every concept discussed here has a separate syllabus, okay, a separate content which can be studied in a separate, as a separate course, okay. But we are trying to give you an overview about things, so that is why I've confined everything. So after path planning, what we need to study is, we need to study about the torque and force relationship created at the end effector. So for that, you must understand about how the impact is being created when we move the robot with respect to different locations. If we move the robot with respect to a different path, if it is being created, okay. So what is torque, what is force, and why it is very important to be studied? So if you ask me what is force, the force is nothing but the push pull effect created. But should it be studied only at the end effector? If you ask me, it is not like that. We need to know about the torque relationship, torque profiles, force relationship, force profiles created at the end effector as well as at the joints. So it is must for a robot to be learnt. So apart from these, we have one more topic called dynamics. So this dynamics is a very vast area where you can diversify yourself when you are ready for taking up the study on robotics. So why? So dynamics is a complete different study. So we think the robot to be as calculated through the specifications, and if we employ that, will it function after creating a path or after putting up the computation for forward motion, forward kinematics problem, after proposing a solution for that? If you think the robot can function, still we have many problems in it. That starts with dynamics. Why? Supposingly, if I handle a weight for a specification of 1 kg, if it is taken to a different location from the starting point, we may have disturbances created by the weight, which may impact the operation of the robot. That is, I may have the robot planned based on the specifications, but in spite of these, if I try to move the robot, the external forces which is present in the environment, because we live in an environment where external forces are present. The forces can be an interference because of the air dynamics, it may be a force created because of the oscillation of the weight, it may be a force created because of the link structure which is provided in the robot. All matters. So dynamics is a very big concept for studying. So for that, they will prefer Lagrangian mechanics for understanding the dynamics. We are not moving further into the details about the Lagrangian, but since this is an overview about the principles behind robotics, I have started from the introduction part where the word is being coined, and we traveled into the history parts, and followed by that the science behind robots based on the industries. So this is all about the session and the future scope. If you ask me, what can I do when I take this robotics as a study? So you may see about the drone technologies, you may see about different bot mechanisms, you may see about the automated defense mechanisms employed at uh, different country based armies. So all is an example for robotics. So the field of robotics have its roots at different areas, wide areas. It will, and it will have the future, the next upcoming generations will have a major effect where everyone will keep a robot instead of having an animal. So nowadays we have a pet, and in the near future, in the next 10 or 5 years, 15 years, you will have every robot at each home, and this will replace your current pet animals. So this is how it is going to get commercialized, and the understanding about robots is must. Even now we have vacuum bots being employed, the vacuum bots which are present in our homes, which can operate to a different environment, which can sense its surroundings, which can sense what kind of objects are being present, is an just an hinge about the understanding of robots. You know about automated drones also. the automated drones which are given for surveillance, which are put for different areas of application, are also an extension of robotics. So robotics is everywhere and the automation is everywhere. So if you ask me the future of robots and the next 10 or 15 years, we will not only have pet animals to be replaced, even our human, even it will replace the humans in the workable areas where a human cannot perform. So we may not need to send a human for the space. Instead, we will send a robot there, and the robot will operate on the basis, on the intelligence what is being provided. So the future scope is everywhere, everywhere for robotics. So, and this is my end of the session. So it is all about the principles and the basic understanding upon what is robotics and how it works and how it functions. And the focus is more upon the industries. Rather, we uh, discuss about the intelligent robots. In the next session, we will discuss about intelligent robots too, and how the architecture of intelligent robots are being taken, and what makes the robot to be different from industries, and what is the neural scheme behind that, how it is learning, how the learning curve is for the artificial machines and everything. Thanks for listening to my class, and please watch my next video too. Thank you.